is fractional dissociation? Well, if you ever ask yourself the question, how do I express something as either a fraction or a percentage to tell somebody how much a molecule dissociates? That's fractional composition. So for instance, hydrochloric acid, what is it? If you answered it's a strong acid, then you'd be correct. And you also know that the fractional composition, when we're talking about it, we've always said strong acids completely dissociate. But then you have something like acetic acid. Is that strong or weak? It's a weak acid. So what that means is it only partially dissociates. So fractional composition is going to allow us to express what percentage of acetic acid in your solution turned into acid molecules or acetate molecules. And so we're going to be able to express that as a fraction, meaning did 99% of your acetic acid turn into acetate and hydrogen ions, or did 1%? Okay? And so in this lecture we're going to discuss what this is and what are the equations surrounding fractional composition. If you have a weak acid, it is governed by an equilibrium relationship, such as what we see above. So as I mentioned before, we may want to express what fraction of this dissociated. And so that's called the fraction dissociation of an acid. And it's given the symbol alpha. So alpha can be defined just as you would any other fraction. So a fraction is expressing the part that you're interested in divided by the whole, the total amount on the bottom. So alpha in this situation is going to be my part that I'm interested in. So your dissociation of HA can be discussed as either hydrogen ions or acetate ions. But since we're working in water, you're going to have hydrogen ions produced also by water. So we're going to discuss and think about fraction dissociation as the production of my conjugate base. Okay? So my part that I'm interested in is what part is my alpha over my whole, my total. So in this case, my A minus is going to be my part. Okay? So if I think about this in terms of fractional. So then I also have my whole. So what's my whole? You could say, well, that's what's left over, H plus HA. But once again, hydrogen ions come from your solution. So what that means is we need to describe our whole as HA plus A. Because if you add those two together, they should sum up the total things that are in solution. Okay? So we've got A minus plus HA. Okay? But we also talked about labeling this maybe as X. So whenever we talk about KB or KA, we talk about KA equals X squared over F minus X. So if we want to relate these to that terminology, we could. So in our ICE tables, our A we always represented as an X. So we could substitute in an A here. Same thing here for this A minus, we could substitute in an X. But what about HA? In your ICE table at equilibrium, you always end up at the end with F minus X. Okay, because that's the equilibrium relationship of HA at the end of your ICE table. So could we further simplify this? Yes, we could. So alpha equals X over F, where F is your formal initial concentration of your weak acid. Okay? So let's do this exact same thing then for a base. We also want to talk about our fraction of association of a base. So if you have a similar equation here, your equilibrium expression, we can then do the same thing and talk about the association of a base, meaning what fraction of it is in the associated form. And so that's why it's given a different type of name, but it's the same symbol. And we're still representing it as part over whole. So our part in this case is our HA. All over our HA plus our A minus, just as we did before. Okay, so the main difference here is now we're talking about the association, but you can still think about it in terms of X over F.